We've arrived at chapter 13, and we're going to get into one-way analysis of variance, often called ANOVA. And there's different types of ANOVAs. We're going to spend most of our time looking at one-way ANOVA and factorial two-way ANOVA. But ANOVA, again, the term analysis of variance is exactly that. We're going to somehow analyze variance to determine whether or not there are significant differences between three or more means. I know it sounds a bit complicated, but we're going to drill down with this section here and unpack some of the theory behind analysis of variance. After we do the theory, what you're going to get a chance to do is to actually run an ANOVA using SPSS, and I will show you how to interpret what an ANOVA output is, what to look for. We'll talk about things like post hoc tests, and then how does one write up a statistical conclusion for ANOVA. And we'll do that for one-way ANOVA, and also in part 2, we'll do that for factorial ANOVA. So the learning goals of chapter 13, again, we're going to get into not only what analysis of variance is, how it operates, but when it's appropriate to use it. We'll get into some of the conceptual basis. You're going to get into interpreting what's called an F statistic. It's very similar to a T statistic. There's actually an F table, just like there is a T table. We're not even going to get into the F table. But what I want you to be able to recognize, if you never have to use an analysis of variance in practice, I do want you to be able to recognize what an F statistic is and what it stands for. So you're learning about the numbers that are presented, and then this coding or this symbolism to let you know about what the statistic is actually saying. And then you're going to get some hands-on work using SPSS to complete and interpret the results of a one-way analysis of variance. We'll leave it there. And it's fairly straightforward. Actually, it's very similar to running a t-test, but we do one added step, and that's called a post hoc analysis. And it's fairly straightforward, but we'll get to that when we get to that. This is a bit of an aside here, and before I get into analysis of variance, and I just wanted to draw your attention to what Salkin has put together in his textbook, which can be really, really handy, actually. And this might be handy, for example, later on when you're doing your final analysis project for the course. And he's created a series of flowcharts, and these are like decision-making trees, in terms of how do I decide which statistical test to use given the data that I have. Actually, not so much given the data that I have, but definitely given the type of research question that I have. And so we're getting to more complex ones here. I think he has this at the end of a bunch of his chapters. And so I just wanted to draw your attention to these decision trees here, and they're fairly straightforward. You can roll through them. Let's start off with an example. So in our introduction to analysis of variance here, let's say that we wanted to assess the differences in the quality of life outcomes, right? If we could measure quality of life after exposure to one of 4 different conditions. And so here we have, in the conditions that are set before here, we've got, I might have one group that gets 6 weeks of supervised physical exercise, another group gets 6 weeks of CBT, cognitive behavioral therapy. Another group gets the combination of both physical exercise and behavioral therapy. And then finally, I've got one group that receives no treatment. We call this our con or our control group, right? So we have 4 different groups here. And what we want to discern here is there any difference in the quality of life scores, whatever measure we give them, across these 4 groups? And we might have a research hypothesis that says something like, well, we think that group number 3 there, 6 weeks of combined therapy, will have higher quality of life scores compared to those who in physical exercise, who might have higher quality of life scores compared to those in the behavioral therapy, who might have higher quality of life scores compared to those who get no treatment, or something like that. Sometimes we may go, we're not sure where the difference may lie, And so we're just going to do some exploratory work here. And so we think there's going to be some differences, but really we're not sure. And so you're going to set this up just like a t-test. You might have more than one hypothesis, though, in this case, but it's okay. You can solve that using analysis of variance. Sometimes when we do analyses, what we like to do is use the things that we are familiar with. And so you all know how to run dependent and independent t-tests now. So you might ask me, well, why don't we just run a series of independent t-tests? Here we go. If I were to find out where all the differences lie across these different groups, it would take about 6 independent t-tests, which is not, a lot to do. It wouldn't take that long to do. So you could do that technically, but there's a problem with that. Running multiple t-tests incurs a bit of a danger, not a danger, but it presents a problem, and that problem is I'm going to discuss on the next slide. Herein lies the problem. When you run more than, it's tough to say how many t-tests you're supposed to run or not. Generally, you don't want to run more than 2 t-tests. That's being pretty conservative with respect to that. On one sample set of data, right, you don't want to run probably more than 2 t-tests. So especially if I've got 6 different t-tests, that's a lot more than 2. And if you run more than 1 t-test, what happens is you have a greater risk of making a type 1 error, right? And so we call this the inflation of alpha. Remember what alpha was. Alpha is the same thing as setting your level of significance, right? At the beginning of every study, you say, well, I'm going to set my level of significance at 0.05. And so that means I'm going to accept a 5% chance that any differences I see happen by chance. That's going to help me discern whether or not to reject or accept my null hypothesis. But there's an additive effect if I run more than one type of test like that, each with its own level of significance. Each one of those levels of tests that you ran, those independent t-tests you were going to run, all 6 of them, each one of them had its own level of 0.05, and those things begin to add together. So the data is here in terms of how we sort this out. This is the formula here in the center, right? It's this formula here to determine the chance of making at least one type 1 error. And so we work this out. It comes out to, if I run 6 independent t-tests and I have my level of significance set at 0.05, now there's a 26% chance I'm going to make a type 1 error. And the thing is, you're not going to know where you're going to make that type 1 error in those six tests. So it makes things even worse, right? You might have created an error. I mean, that's a 5 times greater chance of making a type 1 error because you're doing multiple t-tests. And so we call this the inflation of alpha, and it's a problem. There are some things you can do with t-tests. So say, for example, you're running 3 independent t-tests, which isn't unreasonable. You can do something called a Bonferroni correction factor. I'm not covering it in this course, but it is something that you can do. Or you can run, if you've got 3 independent groups, the easier thing to do and the much more efficient thing to do is to run a one-way analysis of variance. I think I explained this on the previous slide, so I won't say anything more about this slide here. A one-way analysis of variance will do this. It'll let us discern where a significant difference exists in multiple independent groups. That is to say, three or more groups. And so the variables get a little bit interesting now because we have to start talking about grouping variables and testing variables. And we kind of saw that in t-test. And so you're going to have 2 different types of variables you're going to use with one-way analysis of variance. And the first one is a nominal, or what we call a grouping variable. Okay, so if I have 4 different groups and they're from 4 different provinces, that would be a nominal type of variable. If I wanted to compare people from BC, Alberta, Ontario, and Quebec as an example, that would be my nominal variable. These are my grouping variables. And the other variable is the one that we measure. This has to be an interval or a ratio variable, okay? So it's got to be a continuous variable of some type. One of the reasons is you can run means off it. It just simply doesn't work with the mode or the median, right? So you have a nominal, or what we call your grouping variable, and you also have your continuous variable. That's the measure that you use, And just like with every statistical test, the first thing that we do is we set up our null hypothesis. So in this case here, on this particular example on this slide, we have 4 different means, and what we want to do is determine whether or not there's a difference somewhere across these means, right? Analysis of variance proceeds in 2 stages. The first stage is there a difference somewhere across the means, yes or no? And then the second phase is, okay, where are those differences in particular? And so this is our null hypothesis, right? And again, remember what we do with statistics here. Even if I see large differences between group means, we have to understand that those differences that we see still could have happened due to chance. Okay, and we actually have to disprove that it happened from chance in order for us to say that a significant difference occurs, right? So this is what we do with null hypothesis. We set up our null hypothesis, and then we use ANOVA to either see whether or not the null hypothesis holds or whether the null hypothesis doesn't hold. This is a bit of a visual diagram, again, showing that just like with t-tests, one-way analysis of variance, we are collectively asking about differences between distributions of scores. And of course, with every distribution, we have our mean scores, and we have some aspect of dispersion of scores. Okay, so here's two different groups. At the top here, we have 4 different means, but notice what's happening here. The means are really, really close together. Now, there's going to be individual differences between those means. They may not be that large, and so even at a visual, from a visual perspective, you can probably go, yeah, highly unlikely that there's any significant difference between the means. It gets a little bit more interesting when we see that when the differences become a little bit larger between the means, and now we're saying, okay, now this is getting a bit more interesting. Maybe there's no difference between these 2 means here, but there might be a difference between the first mean and the third mean, the first mean and the fourth mean. We don't know where all these differences lie. And so it sounds like one-way analysis of variance is going to be complicated. It's not. Here's how it actually runs. Number one, one-way analysis variance does 2 things in sequence. The first thing is it's going to tell you overall whether or not in this group here a significant difference exists. Okay, we'll talk about that. That's the first thing it's going to tell you. And if there is a difference somewhere in between the means, the first stage doesn't tell you where the difference is. It just says there is a difference. Then you go to the second stage of analysis, and a one-way analysis of variance can tell you where that difference lies. So it may come out and say, yeah, you know what, there's no difference between these 2 means, but there was a difference between the first mean and the third mean, the first mean and the fourth mean, and also the second mean and the fourth mean, and there really was no difference between the third mean and the fourth mean. That sounds all kind of, pretty sketchy the way I'm talking about it. It's actually hard to keep it straight in my head, but there are some tables that are pumped out that you can take a look at, and one-way analysis of variance will discern that for you, and I'll show you how that's done. How does ANOVA let us know whether or not there's a difference across a series of means, right? Or more than 3 means. And one way to envision this or to conceptualize it is to go back, like we did with t-test, and use the signal and noise example. We're always looking for the signal. And again, the signal represents some kind of systematic influence outside of chance that is responsible for any of the differences that we see across the means. Well, we know that chance alone can cause differences, and so we think there's going to be a signal there. Now, the thing is, the signal may or may not be there. We actually have to partition out that signal from all this random noise. And you might want to think about this random noise as random variation. We'll call it within groups variation coming up. And the signal is part of what we call between groups variation, right? Because I'm looking for differences between the groups, and maybe there's something that's causing that difference that we see between the groups. That's the signal that we're looking for. And so I'll use terms like partitioning out. That's kind of the phrase that I'll be using as we move forward. We're going to partition out variance from variance to see whether or not there's a strong enough signal to let us know that a significant difference exists between means in 3 or more independent groups. what kind of partitioning out or accounting for the noise are we talking about here? And I've put it into three different sentences here to kind of describe that for you. If I can be frank with you, one of the better things to do to understand this would be to work through a handout that I have posted in Moodle, and it's a bit of a long one, and it takes you through all the mathematics. And so that's just a bit of a heads up, it's coming, and this sort of describes what's going on there. But here we go. So what type of noise are we talking about that we have to partition out? Well, we know there's going to be some variance between all the individual scores and the group mean. Whatever group they're in, there's going to be some difference. We know what that is. That's going to be the standard deviation of that particular group. But you know, what if I were to take a mean of everybody? If I've got 3 different groups, there's 10 people in each group, 30 people, and I were to take a total mean of all 30, despite the fact they're all individual groups, I'd take what I call a grand mean, right? I've got my grand mean, and then I take a look at the differences between each group mean and how they're different from this grand mean. Okay, and that's coming up. I'll describe that a little bit more so. That's the second type of noise we're trying to clear out. The third part is, again, between all the individual scores and the grand mean. That's the other type of noise. And so we work with these aspects of noise here. And whatever variance is left over, if it's large enough, this is going to be the signal that says something else other than random variance or random chance caused the differences between the means, if there are any. Let's look at an example then. And I have this in an MS Word doc for you. So a lot of what I'm covering here in these slides, I've put together in a Microsoft Word document using this very same data that I'm about to go through with you. So if you get lost in this presentation, you can access that as well. But let's do an example together. So here we go. Let's say that I want to develop a drug that elevated the mood of statistics students, because we all know that stats can affect our mood, right? And probably not so great. So we do, and we'll call this drug Mood Enhancer because we were really creative when we came up with that title. We have 30 students in the class, and so we randomly allocate them into 3 different groups. Again, we do random allocation because we don't want to inject any bias. And lo and behold, we're going to find out that we've got 10 in each group. I'm keeping this thing really sanitized for us. It's never that clean. Regardless, we have our 3 different groups. So group 1 is going to be our control. They're not going to get any drug. They may get some sort of placebo pill, for example. Group 2, we'll call them ME1. They're going to get a low level of the mood-enhancing drug because we actually think there's going to be some sort of dosage effect here. And of course, group 3 gets the high level of the mood-enhancing drug. And here is our hypothesis. We're really sold on this drug that we've developed, and so we think, and we also think there's going to be some level of a dosage effect. And so we said we think that the higher the level of the mood-enhancing drug that is used, the greater the elevated mood, assuming that the scale doesn't go beyond the scale that we're going to be giving them. And so here's our research hypothesis. ME2 is going to be greater than ME1, which is going to be greater than the control. And of course, the null hypothesis would state that there's going to be no differences between the mood scores across these 3 groups. We should talk a little bit about the mood scale we're going to be using. And so it's a highly scientific scale here that I made up, and it's a mood scale of 1 to 10. And it even goes to 1 decimal point. You don't know that, but I just had to do that to add in a little bit of variance so my example will work. But in essence, on the left-hand side here, low score means we're feeling very lousy, and then on the right-hand side, there's a score between 9 and 10, so I'm feeling amazingly great, and everything else in between. So, I mean, a lot of times with surveys, you'll actually have numbers anchored to qualifying statements, so the individual who's answering the survey knows exactly what the numbers mean. I just kind of ran out of space here, so I just kind of wanted to give you a bit of the lay of the land in terms of how this mood scale works. let's describe this partitioning of variance out a little bit more. And there's two different types of variance that we deal with ANOVA, which is kind of nice. There's only two. And the first one is what we call within group variance. And I always look at the terms themselves to give me some clues as to what exactly these terms are trying to describe. So when I see within group, that means we're talking about the random variance that occurs inside an individual group. Remember, you've got 3 or more independent groups, and so within group variance is all the variance that's happening inside an individual group, right? This is that random variance that can occur. Between group variance is a little bit different. When I take a look at the term between group, now we're looking at the variation, right, or the differences between these group means, right? We're assuming we're going to see differences across these 3 or more group means. And so we call that between group variance. And what ANOVA does is it creates a ratio or a fraction using within group variance and between group variance. And that will be described in the slides coming up. This first aspect of variance, within group variance, is expressed as, and you'll see this in the textbook, you'll see it elsewhere, as SS within. Okay, and SS stands for sum of squares. I'm not going to describe that. This really is more of the mathematical machinations that are going on. I do explain it actually more so in the handout for this unit. You'll see how within group variance is calculated and between groups variance is calculated. And there's a better description of what we call the sum of squares within. But let's take a look at the definition of within group variance, and we call it this natural, inherent, or random variation that exists among all individuals, right? Let's say that we were all together in a real class, and I were to give you my mood score or my mood test, and you were to answer. I would ask you, what is your mood today, and you would give me an answer. And all of you leave and you come back on the Wednesday, right? If we had the class on a Monday, we're all back together on a Wednesday. And I give you the same test. Would your mood be the same or would it be different? For some, the mood might be the same, but for a lot of folks, the mood might be a little bit different. Now, what caused that mood between a Monday and a Wednesday? Who knows? It could be all kinds of different things. And your mood score might not have changed a whole lot. Some it might have, fluctuated wildly. For others, it might have been, 1 point above or one point below. And so this is the whole point of within group variance, right? Or this random noise aspect is our mood fluctuates, right? It fluctuates during the day, right? I mean, I could measure you in the morning at 6 o'clock. If you're not a morning person, your mood might be really low. Might measure you at 3 o'clock in the afternoon. You're a day person, right? And your mood is much higher. So there's all different kinds of reasons as to why mood might fluctuate. And this is why we call it this random or inherent variation. And this is what I mean by random variance across a week. So this is just kind of off as an aside. This is if we're on the freeway here, we're all making a pit stop at a gas station. Just don't have the coffee. I found that coffee at gas stations can be subpar. So don't have the coffee. Anyway, here we go. So let's just say I have three students here, and I had the time and they were willing to do so, and I just measured them on my mood scale, right? This is outside of our study. This is, again, we're not in the study right now, and I just wanted to measure them. So I asked Bob, and every day Bob gave me his mood scale, same time of day, and so we see that Bob's mood well, he's fairly stable except for Thursday, a little bit of an off day on Thursday, but Bob's got a little bit of variance there, but his average is a 6.52 out of 10. So he's not doing great, but he's also not doing too poor. And here's his standard error there. Mark seems a little bit more buoyant across his days, and we see he's got a much higher mean score. And again, look at his standard deviation is smaller, so Mark doesn't vary much with his mood, does he? But the thing is, he still does vary, right? And then we have Sue. Sue's pretty consistent. And then on a Friday, she suddenly drops down to a 6. Well, this is kind of uncharacteristic of Sue. So who knows what happened on a Friday? Maybe her weekend plans got got canceled. She had forgotten she had a Mike Bodner midterm on that morning, had to rush to school and write it. So she wasn't doing so great on that particular day. We don't really know what happened. Or it could simply just be no reason at all, right? I mean, sometimes you just don't have an explanation as for why things change. So her mean was, close to 7, and she again had a fair amount of variance, almost the same amount of variance that Bob did, right? I mean, I could add them all up, for example, and what I find is, the on average, their daily together, they're all around about a 7, pretty close to it. Now, again, these averages here don't tell us the real story because we have some fluctuation here, right? So they're the entire, here's your grand mean. If I were to add up all these scores here and take a mean of all their scores for Bob, Mark, and Sue over that week and measure them, I'd get a grand mean of around about 7.09 with a standard deviation here. So again, this mean here might best reflect what their average scores are for mood. The point is, moods fluctuate and things fluctuate, and this is an example of random variance down to the individual. Look, Bob oscillates a little bit. He goes up by 0.8, from Monday to Tuesday. From Tuesday to Thursday, he drops 1.4 points. We see the same drop in for Sue and Thursday from 7.4 to 6. That's a drop in 1.4 points. Mark's pretty good. He doesn't deviate that much. And so there's all this random variance going on. I mean, what would even cause a difference between a 0.2 between Mark's scale here, 7.5 to 7.7? Who knows? So you have this is what I mean by this random inherent variance. I'm sorry for a long slide, but I wanted to give you another example of what I meant by that. Now, the between groups variance, again, we have here at the top, you'll see it expressed as sum of squares between, right? This is the variation between groups that is caused by some sort of external systematic influence. I like that term. I kind of made it up this year. At least I think I did. Maybe I borrowed it from somebody. I don't know. But I kind of like it because it's broad enough that allows us to talk about anything as long as it's systematic and we know it's external to the group. So we know it's going to be something that's going to cause an effect. We often call that the independent variable in the research vernacular, right? And so, so this between groups variance is something that is in addition to the random or the within groups variance that is already present. Okay, so the between groups variance combines the within group variance or this random variance plus this treatment or intervention variance. That's what the between groups is. It's not just the intervention, okay? It's not just the intervention variance. It's the random variance or within groups variance plus this systematic or interventionist or treatment variance. That's what the between groups variance is. Okay, so let's take a look at the data then. So we've got all this preamble to our example here, and I'm going slowly on purpose. Also, I've only had 1 cup of coffee today. That's another reason why I'm going slowly. But let's carry on. So I've kind of put some data together for us here. So here we have our group 1, our control group. And look, each one of those groups has a sample size of 10. Isn't that lovely? Nice and sanitized. Believe me, it never works out that way in real life when you're doing random allocation. When you see perfect sample sizes in each one after they say random allocation, I always look at it a little bit sideways. But that's for another lecture. So here we go. So each one of those 10 people gave their score on that day, right? This group here had no mood-enhancing drugs. Second group, group number 2 did a little bit, and group number 3 had a little bit more. And so we see in the bottom here these different group means. So the group mean of the group 1, who had nothing, was 6.81. They're almost a pretty happy group. Look at group 2. Group 2 is a little bit happier in terms of their mood. Their mood's a little bit more buoyant. And look at group 3, 8.32. And of course, we have their standard deviations and the measurements of their group variance down below. Right? So let's go on to the next slide and unpack what we see, and we'll put some words to it. Now, what we saw in the previous slide, you can go back and take a look at it, is we saw a particular trend that was occurring. If you noticed, the mean scores of the moods for each one began to increase, right? The control group had the least amount of had the least highest mood score. The middle group had a score that was a little bit higher, and the third group, who had the highest amount of the mood-enhancing drug, had the highest score, right? So the scores seem to be increasing. Now the question is did these increases in scores that we see, is there really a true difference there, or did these differences simply happen by chance, right? But now we have to ask the question a little bit more deeply. So what might be causing things if it was by chance, right? So the increase in the scores may simply be due to random variance, right? This within group stuff that we've talked about. But they might also be due to the extra variance that was brought about by the addition of the mood-enhancing drug, okay? So this is where you start getting into this random stuff and then the added variance. This extra variance that we're talking about here is the systematic influence. We expect, right, this is what we hypothesize, that the systematic influence is going to cause a change in the mood scores. And if I talk about change, I'm talking about differing scores. I'm talking about adding in variance, because the root word of variance is vary, or to vary, which means to move away from something, right? So this is what we're talking about here. And so this is what ANOVA does now. Now ANOVA goes and partitions out this added or extra variance, if it exists, right? It partitions it out. And if a large amount of this extra variance can be shown, then it means that the changes in the mean scores were likely due to the mood-enhancing drug and not just due to random variance. And so analysis of variance starts at a particular place. And it starts with this. ANOVA will calculate for us. Now, you're not going to see this. SPSS is doing this for you. However, you will see it if you go through one of the handouts that I've given to you uploaded to Moodle, and we talk about this. There's a total amount of variance out of all the three groups, and we can work out this total amount of variance. And the total amount of variance is the sum, right, of the within subjects variance, with this random variance, plus the between subjects variance. That's what we're talking about. Combined in total, this is going to give us a total amount of variance. Now, you don't have to think about what does that look like mathematically. Simply don't. Think conceptually here for a second, okay? And just acknowledge that there's going to be a total amount of variance in this whole sample set, the sample size of 30. And now what analysis of variance is going to do, it's going to partition or parcel out this random variance and see whatever is left over, if there's enough variance left over to give us an idea of whether or not these differences in the means happen by chance or not. Carrying on with our conception of total variance, let's just take a reminder of what we're talking about here. So what I've put together here on this slide, again, trying to keep things as simple as possible, is again a reminder of what between groups variation is. This is the one that we're kind of interested in. And so between groups variation, again, is going to be some random variation that we know always occurs. And it's also going to be combined with a treatment variation. And we have a maybe on here because we don't know if the treatment variation actually does anything, right? So this is still a bit of a mystery on this side. Nevertheless, conceptually, this is how we describe it. Random variation plus this treatment variation. Whereas down below, within groups variation is simply just random variation. And again, this is always present, right? So we want to try and partition out this stuff here to see if this stuff here is left over. That's what analysis of variance does. What ANOVA does with this between groups variation and within groups variation is it creates a ratio. And this ratio, or it's called an F ratio, is actually something very similar that we saw with t-tests. Remember with t-tests we saw a t ratio. Well, an F ratio is the same as, we could call it a calculated value of F, just like a t ratio was a calculated value of t. And just like with t-tests, what we do is we compare this F ratio, this calculated value of F, to a critical value of F. And just like with t-tests, if the calculated value of F is larger than the critical value of F, then we can say that there is a significant difference somewhere across the means. Okay. Now, you're not doing this comparison. SPSS is doing this for you. But you have to understand how the F ratio is calculated in the first place. You need to know some of the machinery of statistics. So we can start very simply by looking at this ratio here. And all it is really is a fraction. And the fraction is this between groups variation divided by the within groups variation. Okay. Now, remember on the previous slide, we said that between groups variation is this random variation plus this added systemic influence or this intervention variance that we think is causing the difference between the groups. So it's a combination of things, random variation plus this added variance. Okay. But in situations where your intervention or the systemic influence is entirely absent, your between groups variation is the same as the random variation, right? And so we know that if we divide random variation, because that's all that within groups variation is, if we divide random variation into itself, we get a value of 1, and very likely there's no significant difference between the means. You can understand that if we have a lot more of this intervention or systemic influence variation as part of the between groups variation, the numerator is going to be a lot larger, and the calculated value of F, or the F ratio, is going to be larger as well. Now, a small F ratio means that there's going to be no treatment effect, right? We said that's going to be 1. However, let's take a look down here. What if our treatment actually did something? Lo and behold, we knocked it out of the park. We created something that had no side effects, biodegradable if you have any extra, all that type of stuff. And it actually worked. It actually was a mood enhancer. In this case here, the numerator now becomes a little bit different. It becomes random variation plus treatment variation. Okay, whatever these values are going to be. I'm not going to put values to them right now because this is still conceptual. Right? And so on the bottom, we still have the same. The denominator is the same at random variation. However, this value up top here is going to be larger than the denominator. Why? Because I've got this added part here, right? This treatment variation is here. And so the F ratio should be larger than 1. Obviously, if the treatment variation is huge, and this number here goes really high, your F ratio can be pretty large. Sometimes you'll see in a research journal, you might have an F ratio of 34.1. Whoa, that's huge, right? Definitely there's going to be some level of significant difference there. But this is how it works. So this is an F ratio. Now I've combined into the mathematics our concepts of between groups and within groups variation. Now the true F ratio it's a little bit more complicated. It's not just the between groups divided by the within groups, or pardon me, the sum of squares of the between groups divided by the sum of squares of within groups. It's actually expressed as an MS between groups, and the M stands for mean. And so it's going to be the average variance between the groups divided by the average variance within groups. And so this is what this means. So an F ratio is the mean square between the groups divided by the mean square within groups. And I'll unpack that a little bit more. We get some funny things like with degrees of freedom again, and it's a bit more messy, but this is going to come up again. You're going to see a lot of this in a table at the very end. It's a one-way analysis of variance table, and I want you to be familiar with that table. Actually, it'll be helpful for you. Before we get to that table, we need to take a look again at what we are doing here to calculate the mean square sum between groups and the mean square within groups. And so this is they're actually two individual fractions. It's going to be fractions within fractions. It does get a bit messy, but just bear with me. So how do I calculate the mean square between groups? And really what it is, it's the sum of the squares between groups, which I haven't told you how to do that yet. That's on the handout, divided by a value called k minus 1. And k is simply the number of groups that are being compared, right? So if I've got 3 groups, which is what we have here in this particular one, then to find out the denominator, to calculate the mean square between groups, it's going to be 3 minus 1. In this case, it would be 2, right? So our denominator would be 2. Now the mean square within groups is a little bit different. Again, we have the sum of square between groups on the top. On the bottom, we have n minus k, where n is the total number of participants in the study, and of course k is the number of groups. And so to get the mean square within groups, you divide the number of participants minus the number of groups into the numerator. Now, you're not going to have to do any of this, but the math is really simple, that you could set up a program like this in Microsoft Excel. It's actually not that hard. And this is exactly what SPSS is doing. As a matter of fact, the ANOVA table, right, what we call the omnibus table, where it actually describes what the total F ratio is, that actually, the math is actually there in plain sight. It's not going to show you something like this, but the values are there. And I'm going to show that table to you at the end. Well, and here we are at the end. Not quite. We've got a handful more of slides to go through. But this is an analysis of variance table, and there's one that's very similar to it that SPSS gives you, right? And so this table here, again, shows us what we're doing without going through all the math. What I mean by math is all this stuff in here. See this pair, sum of squares between groups? That's math stuff, okay? It's a lot of subtractions and squares and additions. That's pretty much what you're doing. It's pretty easy to do. There's just, if you got a lot of people in your study, it's just a lot of it, right? So if we go across here, right, so we have the sum of squares between groups. This is all the math stuff where we're subtracting and squaring and adding stuff together. We have, here's that term degrees of freedom again. This is for our group, so it's going to be k minus 1. And to get the mean square between groups, again, we simply divide k minus 1 into the between groups, and this is going to give us our final F ratio over here, right? So there's your numerator, mean square between groups, and we get that from this cell here. You're within groups sum of squares without going into the math stuff. Here's your degrees of freedom is the sample size minus k, right? And then to get your mean square within groups, you're going to divide n minus k into your numerator, and that's going to be this here is going to be your denominator, right? So this is one fraction divided by another fraction. We're just expressing it more simply as something here. And I've actually described for you what the sum of squares is down below, and it's the variance calculated by subtracting the mean from each score in a distribution of scores, squaring the difference, and adding all the differences to produce a total or sum of the squared deviations. That's what it is. You'll get a better sense of what that is if you go through the second handout that I posted for you in Moodle. Sorry, just a quick additional slide here. And this slide here, I'm just putting into print what k minus 1 and n minus k is down at the bottom there, but the table remains the same. What I did here was take all this mood data we've been working with, and I actually ran it through a one-way analysis of variance with SPSS. And what SPSS will give me, part of the output anyway, is what we call an ANOVA table. And if you take a close look at this ANOVA table, you'll see that it's pretty much set up the very same as the previous table was on the previous slide. Okay, but let's go through this table. I want to show you a few things in terms of interpretation. Right. So what do we want? What we want is we want our calculated value of F, or our F ratio. Okay. Now to get this, I need to create my fraction, and that's going to be my mean square between groups divided by my mean square within groups. And you can check the math on this. If I divide, and this is what I have here, if I divide the mean square within groups, which is 0.231, into the mean square between groups, which is 5.7, I'm going to get a value of 24.7. But how do I get my mean square values in the first place? Well, we do it the same way we saw on the previous slide. What we do for the mean squares between groups is I take my degrees of freedom, which is k minus 1. We had 3 groups. Minus 1 gives me 2 degrees of freedom. I divide 2 into 11.4, and that's going to give me a value of 5.7. Okay, I do the same thing with within groups variance. I take the degrees of freedom, which is 27, or k minus n, or 30 minus 3, which is 27. And I divide that into the within group sum of squares, which is 6.229, and I get a value of 0.231. Now, I already know I'm going to have a pretty high F value just by looking at the amount of added variance that I see with the between groups. Remember that between groups variance is random variance plus the added intervention or treatment variance, right? And we know that within groups is only random variance. Well, I can see almost a double amount of variance being added to the between groups, right? Because between groups here is 11.401. Part of that is going to be this value here, 6.229. So you're adding another 5.2 units of variance there as part of this. So it makes sense that my F value is going to be large. Now let's get back to our calculated value of F over here. And it's pretty large. 24.7 is pretty large. Now, do you have to go and sort out whether this value is significant or not? And the answer is no. You can if I were to give you an F table, for example, and there's F tables at the back of Salkin's textbook. But I said we're not going to go through those tables. It doesn't make a whole lot of sense given that SPSS does this for you. And so this is what SPSS tells you. You don't have to determine whether or not this calculated value of F is larger than the critical value of F. SPSS tells you already by giving you the p-value under sig dot. Sig stands for significance, right? And the significance p-value here is 0.000, which means your p-value is less than 0.001. If you had set your level of significance at, or your threshold of significance at 0.05, we know that this is much, much less than 0.05. So there is a significant difference somewhere across those three means of mood. Now, this is only the first step of analysis of variance. There's a second step. This first step only tells us that yes, a significant difference exists, but it doesn't tell us where that difference is. We have to go on to the next step, and we'll do that in the next topic. And it's called running a post hoc test. A post hoc test will tell you where specifically that significant difference or differences will lie. And we'll do that coming up. And again, here, just a quick testing regimen in terms of the steps that you would follow to run one-way analysis of variance.